Hello and welcome to Stars, Cells, and God, the show where we discuss new discoveries taking place at the frontiers of science that have both theological and philosophical implications, as well as new discoveries that point to the reality of God's existence. My name is Hugh Ross. I'm joined today by my colleague Jeff Zweerink. I'll be your guide as we explore two related topics. Jeff's going to talk about continental stability. I'm going to talk about what's happening in the Himalayas. But before we get into the discussion, I want to encourage you to subscribe to our YouTube channel, Reasons to Believe YouTube channel. Click on the bell icon so that you can be informed of our new videos that we release on a frequent basis. Learn more at reasons.org or by following us on social media at RTB_official. So, Jeff, what's happening with the continents? What are we learning about the continents?
Well, it's just interesting because I was looking through, the, some of the science journals I look at and some of the more popular, or a little bit more lay level descriptions of them, and just kind of looking for what's out there. And as I was looking through, I ran across this one. It says, "Rock steady. Study reveals new mechanism to explain how continents stabilize." So I thought, okay, that seems interesting. Let's kind of to dig into that a little bit. And what I find is that, to a point you've made many years ago, that there's a lot of new scientific findings that actually affirm two things. One, that the biblical description of how things happened here on Earth is accurate, and just that reveal the fine-tuning of what it takes to make a planet where life is habitable. And I see, as I dug into this, I just saw both aspects of that play out. And I thought it was kind of interesting just to kind of bring up and have a discussion
Sounds great. All right.
Because one of the things that we know is that as I look through here, and as I've worked at Reasons to Believe, is that continents just haven't always been around. They're not a recent phenomena, but they weren't always on the Earth. And what's fascinating is that when we date ages of the continents, for whatever reason, they tend to show up as certain periods of ages. I think one's about 3.3 billion years ago. There's a couple in the 2 billion, one that's closer to 1.5 billion years ago, where it seems like there are these pulses of continent formation that happen. And they're all predicated on active plate tectonics, which I know you're going to discuss a little bit about, or I think you may be discussing a little bit about. But so what's interesting about that is that as they look at the ages, it seems like in this particular study, what they're talking about are these, as they're looking at the continents, there are some of these older, very stable continental formations, and they call them cratons, C-R-A-T-O-N-S. Right. And they typically date in the 3 billion year old range. And so if we're 4.5 billion years, so the Earth formed 4.5 billion years ago, this would be about 1.5 billion years. So in that earlier phase, which when you look at the biblical description, you've got, in the beginning God created and the earth was formless void, darkness was on the surface of the deep, Spirit of God was hovering over the surface of the waters. You have day one, formation of the day-night cycle, so clearing of the atmosphere so we can see the light from the sun. Day two, you have the waters above and the waters below, so the formation of a stable water cycle. On day three, you have land appearing. And so, I don't think that's the sign of the first land, because you'd have volcanic activity and stuff like that. But where now you've got this land that seems to be around for a long time. So this is land that's going to be there for a while. Well, that's kind of just in a very simplistic way of looking at things. That's kind of right about the middle there, and that's about 3 billion years ago is right in that range where you would expect the continents to be showing up. And so that's kind of, or the dating of that kind of affirms that description there. But the new part that I found interesting in this study is that and some of the authors of the study pointed out that they thought for the longest time that continents forming and continents stabilizing were the same process. And it turns out that that's not the case. Right. And part of why we have these really old continental formations, these cratons, is because they form and then they get stabilized. And so, just to give a little bit of overview of how plate tectonics works, that you've got you've got plates that move around on the surface of the Earth, and these plates are being pulled apart in certain places, so new magma is coming up and adding to the edges of the plates, and in other places it's being subducted and taken back down into the earth. And you've got on top of those plates, you've got oceanic crust, and then you've got continental crust. And what makes these cratons kind of remarkable is that they're deep enough that they kind of get anchored down into those plates. So as these plates move around, they move with the plates, but they're stable enough, they don't tip over, they don't melt, they don't get subducted back down into and disappear. So instead of being continually recycled, these cratons just seem to kind of float around on there and really kind of allow other continental stuff to congregate and grow larger. And so they kind of form seeds of the bigger plates, or the bigger continents.
Yeah, and these cratons are smaller than continents. So
yeah, they are. Yeah, I didn't do a specific study to see where they are, but typically, they're on the order of they reach about, roughly on the order of 100 miles down. So they get anchored down into these plates as they're moving around, but they're not. What's unique about them, or what's interesting about them, is that they tend to have a very solid plate, or a very solid part on the bottom that is anchored into the plates, and that solid part on the bottom is what actually keeps them from being allows them to float on top of the more liquid, more malleable liquid stuff underneath. So you've got to have both of those to have plate tectonics. You got to have a more malleable stuff underneath, and you've got to have a very rigid plate that that can sit on top of that and float around.
Well, I like your analogy of the anchor, because it is just like an anchor on a sailing ship. You've got this anchor down, and it just stops the sailing ship from moving.
Right, exactly.
Same thing. This craton basically becomes fixed.
Right.
And stuff moves around it, but it remains stable.
Right.
And it does move, but the continent remains intact.
Exactly.
And it's Australia and South Africa where the two cratons exist.
Yeah, I do know there are ones there, but what I find fascinating about this is that when you look at what it takes to make plate tectonics, not just every planet can have plate tectonics, or at least in the fashion that we do, because critical to plate tectonics is you've got these rigid plates and you've got malleable surface or malleable materials underneath, and how that actually requires certain types of chemical structure, and it's just a little bit counterintuitive for how you would expect rocks to behave as they go down.
I remember you wrote an article years ago making the point we got the crust, we got the lower mantle, the upper mantle, then we got the asthenosphere.
Exactly.
And you need all to be highly fine-tuned in order to have long-lasting plate tectonics.
Yeah, because if the plates are too thick, you end up getting these plates that are locked together, and that tends to happen on smaller planets. And if the plates are too thin, they move around far too rapidly, and you get just vastly more plate tectonic activity, which earthquakes and volcanoes, which tend to be a little bit destructive to the life that's around.
A little unpleasant.
A little bit unpleasant. So what this research was able to do, though, is to kind of look at how would these continents stabilize, and part of what play in there, and the fact that it happens earlier, is that the earlier in Earth's history, the more radioactive isotopes there are on the planet. These things tend to have lifetimes on the order of hundreds of millions, billions of years, and so as the further you go on, their activity's less, and so in that 300 billion year ago range, the activity would have been
3 billion year, right?
Did I say, 3 billion year?
Sorry.
I think I said 300 billion year, didn't
Right.
I? That's a long time. In the 3 billion year ago range, the radioactive activity was about twice what it is now. And so that means that you've got all of this radioactive material in there decaying. Where it decays, it generates heat. Where it generates heat, it softens rocks and it makes them more malleable and fluid, and they tend to be more instead of being stable structures, they tend to be unstable structures. Well, what this group was able to show is that what happens is that on the Earth, what had happened is you've got these continents that are forming. The radioactive materials are getting washed off of the continents through rain and rivers flowing. It's not just wind blowing around, so it's referred to as subaerial weathering. They're taken down into the oceans where they get incorporated underneath the crust. As they come back in, all that they're radioactive isotope rich in that environment. As they get put back in, that heats things up. But in the process of heating things up, the melt there is actually less dense than the rocks, and so it floats up to the top, which does two things. That process of melting allows it to concentrate the radioactive materials. They float up to the top. You end up getting granites and very silica-rich stuff. But it removes a lot of that heating from the lower part of these cratons, which now allows them to solidify very hard and provide that thermal barrier so that they don't keep getting dissolved and just reincorporated back into the asthenosphere or subducted, taken back down into the earth. And it happens right at that time where continents now become stable on the earth. And so I just kind of see this confluence of continents forming about the time period where you would expect from a simple kind of reading of Genesis. And not only are continents forming, but the radioactive activity, the process of the subaerial weathering, bringing the radioisotope-rich materials underground to solidify the lower parts of these cratons, so that now you've got not only continents and tectonic activity, but you've got these stable continental structures that stick around and allow for a pretty large amount of continental landmass on a planet that's covered in water. And so, we have 30% continents, 70% water, and that's been pretty stable, at least in more recent, the last billion years for quite some time. And so we see this confluence of two processes that didn't need to work together, but do, lining up with the biblical description, and you make a planet where you've got these silica-rich continents, which are critical for life to flourish. And so I thought it was kind of an interesting, neat new example of how the fine-tuning plays out and how the biblical description
matches. What's really fascinating
matches.
about this paper is basically demonstrating you need aggressive plate tectonics to have stable cratons.
Explain. I think I get where you're going. But
Yeah, because you need all this radioactive material to be coming off the continents into the oceans where that gets subducted, which helps remove the heat from the craton area. Mm-hmm. None of that would happen unless you didn't have this rapid erosion going on and aggressive plate tectonics. That's what actually allows the heat to be pulled away from the cratons.
Well, and it's even, if I've gotten what the paper's saying correct, it's not only does that radioactive stuff get into the continents and weathered off into the oceans, but the process, you've got active enough tectonics that it gets distributed up under those continental masses, and it actually kind of takes more of it out, because as that radioactivity liquefies and melts what's in there, it pulls more of it out of that lower part of the mantle. So it's a pretty strong cycle, not just you kind of got to get it out and remove it. The cycle actually is part of what's removing it. So I think your point's pretty profound there. So.
Yeah, you need the erosion. Now, did the paper make any mention of the role that life plays and getting that radioactive material into the oceans?
No, really, it was talking about was how you've just got these processes that are basically extracting this radioisotope-rich material, weathering it from the surface, getting it back in so that it can be drawn up under the cratons, or under the part that was going to be cratons. So it's just looking at the geological processes.
Yeah, looking at the erosion.
Right.
Yeah, but another factor is that you got photosynthetic life, which is precipitating uranium through the production of oxygen, and that gets eroded out into the oceans. So you need both erosion and life, photosynthetic life.
That's fair. I just know for what they were focused on here is this
Right.
is just looking at the kind of the mechanical processes
I'm just
of
adding
the
up
erosion.
all the fine-tuning.
No, it very well could be.
I mean,
Yeah.
there's multiple fine-tuning evidences in this.
Yeah. Well, and again, part of what I found fascinating in looking at this, and I have realized I use the word fascination way too much, but what I found interesting in looking at this was it wasn't like I had to look very hard to find this. I'm just kind of scanning through some of the headlines of this is finds that other scientists who are just looking at the science have found interesting, kind of summarizing it, or putting together the highlights, if you will. I'm kind of reading through some of the highlights, and it's like, wow, here's another study that shows not only does what we find historically line up with the biblical record, but the process of things that we know are critical for life or here on Earth, that we've got to have active tectonic activity. That's how you get continents form. That's how you get continents that have the nutrients and the kinds of things that life need to flourish and thrive. But this whole process has something that we thought was the same thing, that continents forming and stabilizing we thought was the same thing, isn't really the case. So you can actually have continents that would form, but if you don't have this stabilization process, which is something somewhat external to continents forming happening at the same time, you're just going to get a recycling of all of that, and you're probably going to end up with less stable continents over time. So we may not have as many continents today if this stabilization process hadn't occurred 3 billion years ago.
So that's a fine-tuning feature as well. And what I remember seeing in the scientific literature is, the evidence is overwhelming. We got these long-lasting cratons, but people have been saying we don't know why they last that long.
Yeah.
These
well, now we have a little, at least have an idea why.
Right. So that's what's great.
It is.
It's solving a long-standing problem. So.
And I also look at some of this. Part of what I love about being a scientist is this is just cool. I mean, you think about the process involved there and how elegantly that works. It's just, I look at it, it's like, oh, that's fascinating. There's that word again. That is just so cool how it works. Because it need not be that way. It could just be much more chaotic, haphazard, or what's going on here is destroying what's over there, but it seems to be working in concert to make a place where life can flourish and thrive.
Yeah, you need all that erosion to be there at that time.
Right.
So, and the erosion rate back then was more aggressive than it is today.
That wouldn't surprise me either.
Well, the planet's rotating
exactly,
a lot more slowly. So you get the aggressive erosion just the time you need it. When you got all that radioactivity. Fascinating discovery.
It really is. I agree. So.
Okay. Got anything else you want to share?
No, that's it. I'll throw it over to you.
All right. Well, I'm going to talk about the Himalayas. And, we've been talking about plate tectonics. What we see in the Himalayas and the fact that we could pop up the first slide here, it basically shows you the Himalayas and the Tibetan Plateau, about 1 million square miles. And this is referred to as Earth's third pole.
Okay.
You got the North Pole, the South Pole, lots of ice at the North Pole, lots of ice at the South Pole, but there's actually more ice, at least in the summertime, in the Tibetan Plateau and the Himalayas than there is in the Arctic ice cap.
So the poles, just because of how cold it is and how much water and ice.
So they call it the third pole.
Interesting.
Because it's a huge store of ice.
That makes sense.
But what's fascinating is you got a huge store of ice at a subtropical latitude.
Right.
So it's close to the equator. And actually,
how close to the equator are the Himalayas? Do you happen to know off the top of your
26 degrees north.
Okay. So a little bit further south than southern United States.
Yeah. Yeah, kind of like Hawaii, if you want to put it there. So, but this actually has the biggest cooling effect because the sun's rays are hitting that ice at a more direct angle than, say, what happens to the North and South Pole. I mean, compared to the North Pole ice cap, this has 4 times the cooling effect.
I can believe, because you're getting the direct sunlight reflecting off into the sun instead of the glancing sunlight.
But 2 papers have been published, well, more than 2, but these are the 2 I want to focus on. A paper that came in at the very end of 2023. It was a long review paper. It's this one here, Climate-Relevant Properties of Black Carbon Aerosols Revealed by In Situ Measurements, a review. So it was published in Progress in Earth and Planetary Science, and it's a comprehensive review of what's happening with black carbon aerosols, which you get from burning wood, biofuels, coal, that puts these black carbon particles into the atmosphere. And so this is
so this is just a place where things are burned, but they're not completely burned, and so you end up with black ashy residue.
Right.
Is effectively what this is.
Right.
Okay.
And it's being deposited around the world. And this paper here, which came out just a few days ago in Environmental Research Letters, basically is describing the impact of these black carbon aerosols, black carbon soot, being deposited on the Tibetan Plateau and the Himalayas. And and what they're demonstrating.
Does the Tibetan Plateau have similar sort of ice cover or snow cover to the Himalayas, or is it more
the higher the
ground?
elevation, the more snow you're going to get.
Then that makes sense.
But the Tibetan Plateau, 1 million square miles, its average elevation is 17,000 feet.
Okay.
So it's 17,000 feet. you're definitely going to get long-lasting snow in the wintertime, extending into the spring. It'll start in the fall. So you get a lot of, so the Tibetan Plateau is covered with a lot of snow for several months of the year.
Right.
The Himalayas are covered year-round
Yes.
because they're much higher than 17,000 feet. So, but that's what's called the third pole. And the reason why it's at such a high elevation, we're talking about plate tectonics. You got the Indian subcontinent, thin crust, and because the crust is so thin under the Indian subcontinent, it is able to move rapidly. So it broke off from Madagascar about 50 to 70 million years ago, and then rapidly moved towards Asia. And by rapid, I mean 22 centimeters per year.
Wow, that's brutal. I can't. So effectively, the Himalayas are just a big collision that's happened.
It's a big collision.
And a collision that's still going on. It's
Yes.
I'm impressed by the arc nature of that. It's pretty remarkable how distinct that feature is when you see it in a relief map. So
Well, it is, and the Himalayas basically document the collision boundary
right.
between the Indian subcontinent and Asia. And you're right, the collision is still ongoing. When the Indian subcontinent was over the Indian Ocean, it was moving 22 centimeters a year towards Asia. Now that the collision is underway, it's slowing down to 5 centimeters per year.
Okay, that I can handle.
But that is still a very rapid
fast.
movement. I mean, 2 centimeters is average for the rest of the world. So this is, it's still, and explains why the Himalayas are getting taller and taller, and the Tibetan Plateau, basically what formed the Tibetan Plateau is that this collision basically pushed up all the land that was behind the collision zone.
Right.
So you got these high mountains forming the Himalayan range at the boundary of the collision zone, then behind it, the Tibetan Plateau, and it gets higher and higher as time goes on. And explains why with each ice age in the ice age cycle, each successive ice age becomes a little more than the previous one because the Tibetan Plateau is continuing to go up.
So it can just it can extend cold periods longer just because it's well facilitated too.
So like the last ice age, you had
latitude.
23% ice coverage of the planet, and that's a lot of that's due to the fact this collision is still ongoing. You would anticipate the next ice age would have even greater ice and snow covers than the previous one.
So I presume the fact that you're talking about black carbon and black soot, whereas snow and ice have very high reflectivities, black carbon would have absorbed more sunlight, and that's going to impact things.
There's two effects, and so what this team of Indian geophysicists did is they had 165 stations all over the Tibetan Plateau and the Himalayas, basically measuring temperature, measuring black carbon soot deposition. So they were sampling data from these 165 stations, and they fed that data into a regional climate model. So not a global model. They said, we're just going to focus on South Asia and see what's going on here. And what they notice is that the black carbon aerosols have a cooling effect because less sunlight gets through when you got all these aerosols in the atmosphere.
Okay.
But as the black carbon aerosols and soot falls on the ice and snow, that is a warming effect.
Okay.
So, but what they notice in their model is, and with the data they fit in, is that the cooling effect decreases with elevation. And the cooling effect...
As in the higher you are, the less the cooling effect?
As you go down into lower elevations, the cooling effect gets less and less.
Okay, so the lower in elevation, the less
The lower
the
the
cooling is.
elevation, the less. So at sea level, not much of an effect. Bigger effect at high elevations.
Okay.
And that the black carbon soot deposition that actually falls on the ground, that goes up with elevation. And so it affects the reflectivity, as you would expect, all this black stuff on the ice and snow. And I was quite surprised at the lowering of the albedo. It lowered by 0.04. And to make that clear.
Make that clear.
Okay. When you're at 1, that means you're reflecting everything perfectly.
Okay.
So 100% of the sunlight would be reflected back to interplanetary space. 0 means none of it's being reflected back. So the fact that it went up by 0.04 is actually substantial.
So, I mean, where would the Himalayas be kind of, what is their albedo roughly? Is it, I would assume closer to like 0.8, 0.9, just
Well,
because
if you
they've
had
got a lot of
clean,
ice.
if you got clean snow, it's about 60% is reflected back
Oh,
to
60, okay.
interplanetary. So it's quite a bit.
Okay.
And if you got ice, of old ice, it's more like 50 to 53% reflectivity. So
Okay.
snow reflects better, and fresh snow reflects better than old snow. I mean, if you haven't done any hiking in alpine areas, you can see the older the ice and snow, the less reflective it is. So the fresh stuff, but we're talking between 50 and 60%. But the black carbon soot deposition on these glaciers and snowfields of the Himalayas and the Tibetan Plateau are lowering the reflectivity by as much as 0.04, which means,
So it's about 4% lower
yeah, well, more
compared
than
to
4%.
perfect, but it's already, yeah. So
You're
that's
going from 60% to 56%, or say 50% down to 46%.
Right.
So it's actually like
it's like a 10% change.
about a 10% change, right?
8 to 10% change. So.
So, and the next slide, well, yeah, this slide shows you the Western Himalayas is where you get a 0.04 change. The Eastern Himalayas are the least. It's about 1.5% or 3% change. Western Himalayas 9%, Central Himalayas a little less. But I think this chart shows you why. If you look in the Western Himalayas, you got a lot more land area at very high elevation than you do in the Eastern Himalayas or
Right.
the Central Himalayas. So that's understandable that you get the biggest effect in the Western Himalayas. That's where you got the most land area at elevations of several kilometers. So,
Right.
And they also demonstrated that the warming effect greatly supersedes the cooling effect. You do get some cooling from the stuff in the atmosphere, but the stuff that's deposited on the snow and ice, that greatly supersedes the cooling effect. And the higher the elevation you go, the greater the warming effect. And so it means that you're melting a lot more snow and ice at higher elevations than lower elevations. The other thing they notice with their stations and climate model is that you get more cloud cover at lower elevations, less cloud cover at high elevations. And with less cloud cover, that means you got more sunlight passing through, and therefore the effect of the black carbon soot deposition is greater.
So there's kind of multiple things that are playing into here. It's like how much is in the air, how much cloud cover do you have, and then also how much of that sunlight is actually making it to where it would be absorbed on the sun,
Well, the fact that you
on the
have
snow.
less cloud cover at higher elevations, that's a warming effect.
Right.
So they're basically saying you got a cooling effect and 2 warming effects, but both warming effects greatly supersede the
Right.
cooling effect. And these 2 warming effects actually work together. And so they're saying the warming of the high elevations of the Himalayas is much greater than what anybody ever thought of in the past. So that's what this paper is pointing out. They're also saying that much enhanced warming at higher elevations produces more water vapor. Water vapor is a greenhouse gas.
So it will warm up.
So you
other
actually have
things.
3 warming effects taking place. You got less
So,
cloud
so
cover.
how much of that? I mean, you're down around 30 degrees or less than 30 degrees latitude. So presumably your winds are tending to flow west to east to west. How much? Where? I guess 2 questions I have in that. One, where is the soot coming from? Is it something that is global in circulation, or is it more local? Is part of my question. And then, yes, you're going to evaporate more snow, make it into water, but is that water going to be locally concentrated, or is that going to be kind of blown somewhere else?
All very good questions. And in terms of your first question, look at the Western Himalayas. It's really close to the Ganges Valley.
Okay.
Ganges Valley, 500 million people live there. They're burning a lot of coal, biofuels, and wood. And so you got a lot of this black carbon soot and aerosol production really close to the Himalayas. And so, yeah, I mean, the
So
local
it is more locally driven,
more
almost
locally
entirely.
driven.
That just makes the most sense. It seems.
However, even with their regional model, they said it's complicated.
Mm-hmm.
It's complicated because you got a lot of elevation variation over South Asia,
Right.
and you got the monsoons coming off of the Indian and Pacific Ocean. So they made a significant point in the paper is that we have kind of an idea of what's happening at those high elevations. The impact of all that warming is going to be complicated. It's going to be different region to region.
Right. That does
It
make
might
sense.
explain why, for example, we've been getting a lot of flooding in Bangladesh. I mean, because if you've got warming at higher elevations, that's enhanced melting, which means you're going to have more water flowing down the rivers from the Himalayas. And then if you got, monsoons that being affected, because one thing they made in the paper too is that when you have this warming at high elevation, it reduces global precipitation. And so it means that globally you're going to have precipitation reduce, but they also made the point that region to region, some regions are going to have enhanced precipitation, others are going to have significantly decreased precipitation. So again, they said it's going to be complicated. And they basically end their paper saying, what we've demonstrated is the need for more ground stations and distinct regional climate models. There's been a lot of focus on global climate models. They're saying this is demonstrating the need for regional climate models. And the more regional they make them, the more they're going to be able to help people and say, this is what you can expect from what's going on here.
That's a point one of the people out of our scholar community, Kevin Birdwell, has been making for quite some time. That yes, there are global trends, but really one of the things that we need is local climate models. One, you're going to be able to put more detail into those. The models are going to be more fine-tuned to what's actually going on, so you're going to get better information out of it. But more, to your point, you're going to know what's contributing here and what can we do to help people in that area. So your point is or the point of the paper is emphasizing what Kevin Birdwell has been saying for quite some time.
Well, something they got from their 165 stations is that there's been a dramatic acceleration in the warming effect at high altitudes.
Okay.
Which is understandable because there's been an acceleration of the production of black carbon soot and black carbon aerosols from people in industries in China and India and Indonesia. So they do see the strong correlation, which basically says we know what's causing all this because we're seeing acceleration of warming, which correlates with the acceleration of the production of black carbon.
This seems to point to a strategic point on maybe how to approach some of this, because I've been aware of the climate change discussion, and it seems that by and large in the United States, although I think we're maybe getting a little bit beyond this, it seems to be politically driven, and that once I know somebody's political position, I can make a pretty good assessment of where they're going to stand on climate change and what do we do about it. Which means that we're thinking about it politically as opposed to what does the science say as Christians, how do we deal with it? Those are not the driver concerns. The political position is. But this seems like it may have a way of, instead of putting it out on we need to be concerned about global climate change, having it more interested or of maybe a little bit more focused on local climate change, because those same sorts of things are going to play out more globally, but you're much more closer to this impacts where I am and what's going on. It's a little harder to get somebody interested in what's going on over in another continent when they've got a lot of concerns here. Whereas if you can talk about, hey, this is what's going to impact here and what we can do, it's going to connect more naturally to what people will be very willing to work on.
Well, the paper is basically pointing out that this is a more extreme example of climate change, is that you got the Himalayas warming up substantially faster than they were 20 years ago.
Right.
And and it's causing consequences. You're getting more water flow from the melting. And keep in mind that all that ice over the Himalayas and the Tibetan Plateau, that's from the last ice age. And so that ice has been gradually melting over time. And the melting of that ice has been feeding 20 huge rivers in Asia, which feeds 4 billion people. So it's
That's
like,
a lot.
we need that water, but you also don't want that ice to melt too fast. If that ice melts too fast, you got flooding. And moreover, that means you're not going to have water in the future. And so you really want to stabilize. So we're talking about stabilizing the climate. What we got here is let's stabilize the melting of the ice so that we don't get an accelerated flow, which is going to cause flooding. It's going to disrupt the monsoons season. And, we're already seeing these kinds of disasters happening throughout South Asia.
Right.
And so that should give us some motivation. Hey, we know where the black carbon soot is coming from. It's not coming from South America. It's coming from the Ganges Valley. It's coming from Eastern Asia, Eastern China, Indonesia. And it's already causing a huge health crisis. I mean, one of these starved cells in God, I made the point, you were with me on this one, where in Delhi, the average lifespan is decreased by 12 years on average as a direct result of black carbon soot. And how
That's another point Kevin Birdwell had been making is, we talk a lot about, there's a whole lot of focus on carbon dioxide. Not that there isn't a reason to be focused on that, but there's some low-hanging fruit that not only does it have a significant impact on the climate, but also on health issues. I mean, there may be more strategic places to focus on first while we're working on the longer term
like
problems.
the review paper that I've got here basically made the point, and this is well established in scientific literature. Carbon dioxide is the primary cause of global warming, but almost as significant as black carbon aerosols and black carbon soot. They're number 2 in the list. They're ahead of methane. They're ahead of nitrous oxides. And so, and the point of the review paper is it's a lot easier to mitigate black carbon soot
Yes, it is.
than to mitigate carbon dioxide. So that's an obvious place to go.
Well, and there's 2 positive benefits of that. One, it mitigates climate change, but it also enhances health as well. So it's a win-win in a lot of ways.
It is, because the health costs in China and India to deal with the respiratory diseases that are coming about as a result of exposure to black carbon soot and black carbon aerosols, it's costing a lot of money.
Right.
And so it's like, if you take into account the fact that you got people living 8 years less, 12 years less, even for Asia as a whole, it's 3 1/3 years less. But if you look at India and China, it's 5 years. And in some places like the Ganges Valley, it's 8 years. So that's a huge burden on the economy, having to deal with those health costs. Wouldn't it be better if we could keep people productive for 8 more years, contributing to the taxpayer base? So,
well, that's an odd count. No, you're right. Well, and you look at big things like this, and you do have to make considerations like that. But not only do you, like I said, there's a lot of benefits from not being exposed to as much black carbon. You've got you're healthier. People are just going to be more productive. They're going to feel better. There's a whole lot of benefits that flow out of that really make it an easy target to go after.
What was not addressed in either of these 2 papers is what I think is an obvious solution. Stop burning the wood, the biofuels, and the coal, and burn natural gas instead.
Yeah.
Natural gas is a cheaper fuel source, so you actually have more money in the pockets of everybody if you use natural gas. And there's 0 black carbon aerosols, 0 black carbon soot. And you only get half the greenhouse gases when you burn, you get the same greenhouse gases, but when you burn coal, wood, and biofuels, it's carbon dioxide.
Yeah.
When you burn natural gas, it's carbon dioxide and water vapor, because it's CH4.
Right.
So when you burn that,
that's what you
get water. But the water typically precipitates out, and so it doesn't have any permanent effect on global warming. It's the carbon dioxide does.
It becomes part of the water cycle effectively.
Becomes part of the water cycle.
I would imagine you might even get a little bit better atmospheric cleaning in that you're going to precipitate more, and so you might end up even being able to clean the atmosphere a little bit.
Yeah, people living in the big cities of India and China will actually be able to see the sun, moon, and stars.
Right.
The heavens declare the glory of God. Well, got to get rid of all that black carbon soot and aerosols if you want to be able to see stuff. And so just having a more transparent atmosphere. it means you'll be able to see the building you're trying to find rather than just saying, hey, where is that building I'm trying to walk to? So there would be an aesthetic value in having more transparent skies. There'd be an immediate health benefit. People are going to live longer, and they're going to be more productive because they're not going to be impeded by respiratory diseases. And they're going to have a greater economy because you've got a cheaper source of fuel, and you're going to basically be able to keep the Himalayas in a stable fashion. You're going to have a more predictable water runoff from the melting of snow and ice, and you're going to be able to stabilize the monsoons. So this is going to make it easier to kind of predict where weather patterns. I think it's going to have a huge impact on Bangladesh because they're the ones that have been hit the hardest by changes in the Himalaya snow cover. So
something you've said in the past, just seems to be a great example of it, that in dealing with climate change stuff, that the way the Bible describes things, one, God has created things, and so it's a very robust system, and he's put us as stewards of it, so we have an obligation to care for it well. One of the things you said that has stuck with me is that God cares about the planet and he cares about humans. And so there will be solutions that allow us to do both of those. And this seems just like a perfect example of that. Not only by dealing with the black carbon, we're doing things that facilitate taking care of the planet, but we're also taking care of the people as well. And if God's done things, he's got those situations built into it.
That black carbon soot and black carbon aerosols is also affecting the health of the animals.
That makes perfect sense, yeah.
And animals are very much part of the economy of India and China, so that would make them healthier and again enhance the economy there. And notice God designed the planet in such a way we get huge reservoirs of natural gas. So the solution has been placed there by God in advance. The one thing I think is holding this back is North America, especially Canada and the United States.
How
We're
so?
the problem because we're basically passing laws saying we want to do everything we can to limit the burning of fossil fuels. And so we're actually taking steps to terminate the production and delivery of natural gas.
That's interesting because if I'll just take all of that at face value. We can discuss whether there's some political stuff in there, but by not understanding the problem fully or by looking at it in a small fashion, you can actually implement a solution, quote unquote solution, that makes the problem worse.
Yes. Yes.
So it's not about intention. It's about, do you understand things well enough to understand what's going on in there? Because I think a lot of the people who are making these laws are well-intentioned.
They're well-intentioned. They're just saying, hey, we can stop burning fossil fuels. This will stabilize the climate. What they're overlooking is that, some fossil fuels are better than others. Natural gas is way ahead of coal because you don't have all these particulates and aerosols. You only get half the greenhouse gas emission, and it's a cheaper source of fuel. And the solutions to rid ourselves of fossil fuels entirely are not here immediately.
Right, yeah.
It's going to take time to basically find alternatives to these fossil fuels that are clean, that are not going to have unintended consequences.
Well, and I think to find some of those solutions, there needs to be enough technology around that you can actually use them.
Right.
And so by limiting the burning of fossil fuels, we may be preventing other groups from being able to develop the technological advancement they need to be able to use them. And so it's just interesting to me that a well-motivated solution probably in this instance is actually making the problem worse, which is fascinating. So,
we in North America are sitting on the world's largest store of natural gas. We've got all the natural gas, and what we need to do is make it available to countries that are already suffering from not having access to natural gas.
And enable them to use it in a way to facilitate actually solving the problem well. So.
Right. So let's export the natural gas. It will boost our economy. It'll boost the economy of Asia because they got a cheaper source of fuel. And look at all the money they save from healthcare. Their animals are going to be better, and they get to stabilize the climate zone over the Himalayas and the Tibetan Plateau. Everybody wins. And that'll buy us the time
I think there's some
where
other.
we don't have to burn any fossil fuels at all.
Well, I mean,
So-
I know I was talking with Kevin Birdwell, and he's kind of got some interest in nuclear reactors, and there are solutions out there. They're going to take a while to develop, and so
there are good
we
solutions,
need to be able
but
to.
they take time.
Yeah, and so being able to do things that are making an impact now, knowing that the bigger solutions may come later, is
The
important.
advantage of natural gas, it's a solution we can implement immediately.
I agree.
mean, there's no delay. Well, very little delay.
Very
we
little, yeah.
We have to find some way to get it over to
Right.
India and Asia in sufficient amounts.
Right.
So, well, this has been fun. Thank you for joining us today on Stars, Cells, and God. Join the discussion in the comments below. Remember to like this video and to subscribe for more content. New episodes of Stars, Cells, and God release each Wednesday and are available here on YouTube and on your favorite podcast app. Be sure to share this video with a friend, and remember, the more we learn about science, the more reasons we have to believe in the Bible as the inspired and inerrant Word of God and Jesus Christ as Creator, Lord, and Savior.